Hey guys, welcome back to the channel, and I am back with an amazing question. So this question that you see on the screen is taken from the Putnam competition 2019. If you do not know about the Putnam competition, let me give you a perspective about the exam and how difficult this exam is, and also about how relevant this question is for JEE Advanced. So now imagine sitting for a mathematics exam where getting just one question completely correct is considered an excellent performance. Now imagine an exam where the median score is only 1 or 2 marks out of 120. Welcome to the Lowell Putnam Mathematical Competition, widely regarded as one of the toughest undergraduate mathematics competitions in the world. Every year, more than 4,000 students from universities across United States and Canada, including the institutions like MIT, Harvard, Princeton, Stanford, and Caltech, take this 6-hour examination consisting of 12 proof-based problems, each worth 10 points. In the 2019 competition, there were 4,229 participants, and the median score was just 1 or 2 marks out of 120. Even among some of the brightest undergraduate mathematicians, solving a single problem completely is an achievement. And today, we are going to tackle problem B2 from 2019 Putnam competition. At first glance, the problem looks intimidating. There is a complicated trigonometric summation, multiple cosine terms in the denominator, and finally an asymptotic limit involving n cube. It looks almost impossible to attack directly, but that's exactly what makes Putnam problems so beautiful. They are not testing how many formulas you know. They are testing whether you can discover a hidden idea. Now you might be wondering, why should a JEE Advanced aspirant care about an undergraduate competition? The answer is simple. While JEE Advanced does not ask proof-based questions like the Putnam, both examinations reward the same kind of thinking. Spotting patterns, simplifying intimidating expressions, exploiting symmetry, making clever substitutions, and finding the one observation that changes everything. In fact, many of the most memorable JEE Advanced questions over the years have this exact flavor. They look impossible for several minutes, and then one elegant idea unlocks the entire problem. So even if this exact question never appears in JEE Advanced, learning how to think through it can make you a significantly strong problem solver. So let's begin. So now we have a couple of observations to make here. If you observe, you have cos squared term in the denominator and one more cos squared term in the denominator. So now let us carefully observe the arguments that you have inside the cosine functions. So if you consider a is equals to k minus 1 multiplied by pi upon 2n and b is equals to k pi upon 2n. So when you add a and b, you will get this particular argument. So now let us rewrite the entire summation in terms of a and b. So your k runs from 1 to n minus 1. In the numerator, you have sine a plus b, and in the denominator, you'll have cos square a multiplied by cos square b. And now, whenever you have summations, telescoping is one idea that you should never forget. Telescoping. So what is telescoping? It looks something like this. 1 minus 1 upon 2 plus 1 upon 2 minus 1 upon 3 plus 1 upon 3 minus 1 upon 4 plus 1 upon 4 minus 1 upon 5 plus and so on, plus 1 upon n minus 1 minus 1 upon n. Something of this sort, where all the terms will get cancelled except for the first and last terms. Alright, this is one of the most powerful ideas to solve any summation. So next time, whenever you see a summation, telescoping is something that you should think about. So we are going to use the same technique here, but it is not very evident as to how to use the technique. So let us think of a way. So if we are able to express this particular term in terms of cos square a minus cos square b, and in the denominator you have this thing. So when you split it, you'll get something like 1 upon cos square b minus 1 upon cos square a. So this is how you can split this particular fraction into two different fractions. So now let us go back. So we want to express the numerator in the form of cos square a minus cos square b. So now if you apply the formula of a square minus b square here, you'll get cos a minus cos b multiplied by cos a plus cos b. So you can use the formulas for this and this. I'm talking about the half angle formulas. So cos a minus cos b is simply minus 2 multiplied by sine of a plus b by 2 multiplied by sine of a minus b by 2. And cos a plus cos b is simply 2 cos a plus b by 2 and cos a minus b by 2. So this is what we have. So why did we consider this? We wanted to get a telescoping summation. So that is why we have considered this, and we just manipulated using trigonometry. Now consider 2 sine a plus b by 2 and cos a plus b by 2. That looks something like 2 sine theta cos theta. The formula for that is sine 2 theta. So minus sine theta is a plus b by 2. Therefore 2 theta will be simply a plus b. And similarly, when you consider these three terms, it will become sine of a minus b. Therefore cos square a minus cos square b is this. Since we have sine a plus b in the denominator, so we can write sine a plus b is equals to cos square a, sorry, if you take this minus sign to the other side, you'll get cos square b minus cos square a upon sine of a minus b. So this is what you have. Now let us see what a minus b is from this. So your a minus b is simply minus pi upon 2n. So a minus b is simply minus pi upon 2n. So you can substitute that here. Cos square b minus cos square a divided by minus pi upon 2n. So the 2n will be in the numerator. So when you take this minus sign to the numerator, you'll get something like this. Cos square a minus cos square b multiplied by 2n divided by pi. So now let us rewrite the summation. an is equals to summation k runs from 1 to n minus 1 sine a plus b in the numerator. So sine a plus b is nothing but this particular quantity. Cos square a is k minus 1 pi by 2, k minus 1 pi by 2n minus cos square b is simply k pi upon 2n, and you have a pi in the denominator and 2n is also there. Since the summation is with respect to k, you can bring 2n outside, and in the denominator you have simply cos square a multiplied by cos square b. So you can write that cos square k minus 1 pi by 2n multiplied by cos square k pi by 2n. Alright, so now that's what you have. So an is simply 2n upon pi, and this runs from k is equals to 1 to n minus 1. Let's try to separate the numerator into two terms. So when you divide this term with this particular denominator, you'll get 1 upon cos square k pi by 2n minus 1 upon cos square k minus 1 pi by 2n. Now all you have to do is substitute the values from 1 to n. an is 2n upon 2 pi, 2n upon pi. So first put k is equals to 1, So you'll get 1 upon cos square pi by 2n minus 1 upon cos square 0 plus put k is equals to 2, 1 upon cos square 2 pi by 2n minus 1 upon cos square pi by 2n. Put k is equals to 3, 1 upon cos square 3 pi by 2n minus 1 upon cos square 2 pi by 2n, and this process continues, and when you put k is equals to n minus 1, which is your upper limit, you will have 1 upon cos square n minus 1 pi by 2n minus 1 upon cos square n minus 2 pi by 2n. Alright, now if you carefully observe, this term and this term will get cancelled, and this will get cancelled. Similarly, this 3 pi will get cancelled by the 3 pi that you are going to get here, and this term also will get cancelled. So the terms that remain are, so these are the only two terms that remain. Alright, so your an is nothing but 2n upon pi, and you have cos square 0 is 1, therefore minus 1 plus 1 upon cos square n minus 1 pi upon 2n. So this is the value of an. Alright, so let us simplify it a bit. So an is equals to 2n upon pi, and when you take it to the numerator, when you take LCM and take it to the numerator, your numerator will become sine square n minus 1 pi upon 2n, and in the denominator you will have cos square n minus 1 pi upon 2n. So this is simply tan square n minus 1 pi by 2n, 2n upon pi tan square n minus 1 multiplied by pi divided by 2n. This is what is your an. Now all you have to find out is limit n tends to infinite an upon n cube. So you have to find out an upon n cube. So 2n by pi n cube tan square n minus 1 pi by 2n. Alright, this is what you have to find out. So let us simplify it a bit. So this is 2n upon pi. Okay. So let us simplify it a bit. This n and n gets cancelled. So 2 upon pi n square, and this is simply tan square. Separate the numerator. Then you'll get pi by 2 minus pi upon 2n. Alright. So this is simply tan pi by 2 minus theta is simply cot theta, cot square pi by 2n. Alright, so your limit n tends to infinite. So let us assume pi by 2n is equals to t. So as n tends to infinite, t tends to 0. So therefore limit t tends to 0. So 2 upon pi n is nothing but pi by 2t. So pi square multiplied by 4t square. This is what you get, multiplied by cot square t. Alright, this is what you have. So limit t tends to 0, 8 upon pi cube multiplied by t square cos square t upon sine square t. Now when t tends to 0, cos t tends to 1. Limit t tends to 0. This 8 upon pi cube is a constant, so it comes out, and cos square t is this, and what is left? T upon sine t whole square. So you know that this is a very famous limit, and the value of this is 1. So therefore your final limiting value is 8 upon pi cube. So I hope you understood the solution, and you people are able to appreciate the power of telescoping. So if you like the solution that I have presented, do not forget to like this video, share this video with your friends, and subscribe the channel for more such content. Do check out the other videos on the channel, and I have added the link to my Telegram channel in the description. Make sure you join it. And if you have any queries, comment section is the way to reach out to me. I'll meet you in the next video. Till then, take care.